This problem seems to be pretty easy. All we have to do is compute the energy of one photon of infrared radiation whose wavelength is 1064 nanometers. So computing the energy when the wavelength is given is pretty simple because energy and wavelength are related by this relation. So we know the Planck's constant. Sorry. 34 joule second. And we know the wavelength and we know the speed of light. So all we have to do is substitute these values. And 1 nanometer is 10 to the negative 9 meter. So the units here cancel out. And if we solve this, we will get 0.0186 into 10 to the negative 34 plus 8 plus 9. I'm going to bring this up. So that would be, so this part would be 10 to the negative 17, have joule. So I can write it as 1.86 into 10 to the negative 19 joule. So this will be the answer. Now let's solve 1.2b. So a laser emits a pulse of 1064 nanometers. Okay, so we know it's the same nanometer, it's the same wavelength. A pulse of 1064 nanometer radiation of average power 5 times 10 to the 6 watts. And 1 watt is nothing but 1 joule per second. And this radiation, the laser emits this pulse radiation of this power for a duration of 2 into 10 to the negative 8 seconds. So basically the amount of energy that comes out based on the power and the duration for which the radiation is emitted would be times the time, which would be 5 times joule per second, 2 times 10 to the 8 seconds. The units cancel out, and we get something like 5 2s are 10. So I guess we get 0.1 joule. So that would be the total energy. And we are asked to find the number of photons that are emitted in this pulse. So the energy of single photon is nothing but 8c by lambda, where lambda is 1064 nanometer. And we got this energy from part A, which is 1.8 times 10 to the negative 19 joule. Right, so the number of photons would be 0.1 joule divided by 1.8 times 10 to the negative 19 joule. Now solving this will give us 0.05 times 10 to the 19, or approximately 5 times 10 to the 17 photons.